So today we're going to talk about components of acceleration. So I'm going to start by asking you to consider the following question. Is it possible for an object to be moving at a constant speed and have non-zero acceleration? And if you've been in a high school physics class, then you know the answer to that question is yes. The answer is if we move along the path of a circle in such a way that all our tangent vectors have equal length. Okay, don't forget if you have a vector v, you take its norm, and that refers to the speed of the vector, or the speed of the object, I should say, or the length of the vector. We're going to denote that with just v by itself. That'll mean the length of the vector v. And so you know this is possible because in this particular case, we're constantly experiencing a centripetal acceleration towards the center of the circle that we're sort of moving around. Okay, so I'm going to introduce you some notation here and so forth, make a few statements, and we'll go from there. So let's let a vector t be a unit vector in the direction of the vector v, your tangent vector. Okay, this is a unit tangent vector. The vector t, that is. So what that means is now we could re-express the vector v. We can use this fact. We can say the vector v is equal to the length of vector v times the unit tangent vector in the direction of v. And that makes sense. The unit tangent vector would be in the same direction as vector v is. And if I multiply the unit tangent vector by this scalar quantity norm v, then I get a vector that has the same length as v. So this equality makes sense. All right, so you're just going to follow me along for a ride here, and then we're going to end up with is a good look at the components of acceleration. All right, so let's, for a minute, take the derivative of this. Suppose we wanted to know what the derivative of the velocity function was. Well, there's a bunch of rules about differentiation and so forth of vectors times scalars and things like that, but the product rule, as we would think of it, applies here. So this expression is yielded. But we also know that if we're going to take the derivative of the velocity function, we could also call that the acceleration function, or the acceleration vector. So here we go. Now, what you see here is you actually know something about this vector t prime. So let me just remind you for a minute something that you may not remember, but the following, that if a vector, or like some kind of vector function, r of t maybe, has a constant length, then we know the following. We know that r prime of t is perpendicular to r of t. We've proved that before. So what that tells us is that, if you think about it, this part of the acceleration function, you'll notice, is in the direction of the tangent vector, while this part of the acceleration function is in a direction perpendicular to the tangent vector. So this sort of means that we're sort of breaking up the acceleration vector into two vectors. And you might want to think this is sometimes referred to as this piece here is called the tangential component. I'll just put a E there for a minute, just noted that. And this is sometimes called the normal component. Okay, normal meaning perpendicular, just like it always has. All right, so let's recall a few more facts and see what we can come up with. So we've talked about curvature before. Curvature can be thought of like this. Okay, where r is the path of the r is the parameterized function that describes our motion around the circle, or any path that is. Okay, so we can write it this way using my new notation. Okay, but r prime, this thing on the bottom, is really v. R prime, if r is our position moving along a path, its derivative would just be velocity. And notice this is the normal velocity, so I'm using my new notation here. This this v here means the norm of the vector v is what it means. Okay, and then on top you have this, equaling k. So if we take this last part of this statement, what we end up with is the following, that the norm of the tangent vector is equal to k times v. Okay, so let's go back to acceleration again. We're going to write acceleration again. Here it is, acceleration, v prime. There it is. We said that's our tangential component. And then we had v times t prime. Okay. So, what do we know? Well, we know the norm of t prime. We know this fact. So what that means is I have an opportunity here to rewrite this part of the expression. And that's what I'm going to do. I'm going to rewrite this. This is v prime norm t plus v times, and I want to put kv here because of this expression, but we know right now this statement doesn't make sense because what you have here is you have a vector quantity here. We refer to it as the tangential acceleration, or component acceleration in the direction of the tangent vector. But then over here you have a scalar quantity, so this needs to be a vector quantity. But we're lucky in a sense because we know that we've defined something called the normal vector. And the normal vector is in the direction of t prime, but it's of unit length. So now if you think about the vector I just put in these parentheses, this vector right here, that's really the vector t prime. That's what it is. Actually, I left my vector symbol off up here. Let's be careful. All right, this is the vector t prime. And now why is that? Well, we've already shown that the norm of t prime is k times v. And then we know the direction of t prime is in the same direction as the normal vector n, but the normal vector n here has unit length. So that means the length of the vector kv times the normal vector would be kv. It's in the direction of t prime, so that's really t prime re-expressed. Okay, so what does that tell us? A little bit of simplifying here. We have this plus kv squared times the normal vector. All right, so let's do a little bit more. All right, as we said earlier, we said we could think of the vector v as its length times the unit tangent vector in the direction of v. All right, so now this is going to seem like magic, and all something very nice happens. So let's do v dot a. We're going to take the velocity vector and dot it with the acceleration vector. Okay, so that's going to equal vt dot v prime t plus kv squared n. Okay, so that looks pretty good. But then we can distribute this because we know dot products distribute over sums of vectors. So we get v prime times t dot t plus, and we get this expression, kv cubed times t dot n. All right, a couple more realizations and we'll have something very nice. Well, you know that t and n are perpendicular to each other, so that dot product's 0, so this whole term is 0, so you don't have to worry about that anymore. And then we also learned that if you take any vector and you dot it with itself, you end up getting the following. And it's actually the norm of that vector squared. That's one of the things that we proved. Or you could think of this as what one of dot product's definitions is. It's the norm of the first vector times the norm of the second vector times the cosine of the angle between them. But since these vectors are in the same direction, the angle between them is 0, so the cosine of 0 is 1. The norm of each of these tangent vectors, their unit tangent vectors, are 1, so it's 1 times 1 times 1 is 1. So this whole thing just turns out to be 1. So that means that when we're all done here, we end up getting this expression, v dot a equals v prime. All right? And then if we divide by v, which we can do, we end up getting that v prime equals v dot a over v, or we can write it this way. The acceleration tangentially is v prime equals this nice expression, which you may notice, that's the scalar projection right here. It's the scalar projection of A onto V. And that makes good sense. We would say that vector V has, it's in the direction of the tangent vector, or vector A has a component in the direction of the tangent vector and another component in the direction of the normal vector. This is the expression for it in the direction of the tangent vector. All right, so moving on, let's go talk about the component of the acceleration in the normal direction and its length. Okay, so what did we have? We had acceleration equaled, and we go back to the expression we had earlier, we had this expression right here. Take a look at it. There it is. And then we rewrote it carefully like this. So that's the version I'm going to grab and take with me to a new page. So we'll copy that, we'll go to a new page, and we'll put it there. Okay. So let's talk about just the norm, the length of the acceleration. So now what we've shown is the length of the acceleration vector. We have a tangent, the length of the vector here, the tangential component, plus this normal. Okay. All right, so now what? Well, what do we know about AN? We know AN is kV squared. And how do I know that? Well, if you look at this piece right here, actually, I'm just going to focus on this for now. Just worry about AN for the time being. If you look at this piece here, the normal vector has length 1. We know that because that's what it is. It's a unit normal vector. So that means the length of this whole vector circle in blue is just equal to kV squared. All right, well, k is the curvature, and v squared is what it is. So let's just sub in some stuff and see what we get. So we get AN equals the curvature, which we know to be the norm of the cross product of the first derivative of the position function with the second derivative of the position function over the norm of the first derivative of the position function cubed. V squared is just this. V, don't forget our notation. Okay, so V stands for the length of vector V. V squared would be this expression, the norm of R prime, quantity squared. So that means we have the following. We have an expression for the length of the vector in the normal direction, the length of the acceleration vector's component in the normal direction. So here you go. You get this piece. Over that. Okay, so that's how we can look and think about acceleration vectors, as we could think of them as having two components written like this. That's in the normal direction, and in the tangential direction we had the following. We had R prime dot R double prime over the norm of R prime. All right, thanks for watching.